In today's video, I want to show you how I went about solving exploit number 8, Lucky Spin, found here on the Solidity Challenges repo. So go ahead, clone your repo, and then open it up in your editor. I'm over on the README, and it states that, welcome to Lucky Spin. In this contract, players can test their fortune by guessing a random number between 1 and 100. A correct guess earns a reward, but there's an underlying twist that you need to uncover. And then our mission, uncover and exploit the hidden vulnerability to drain all the funds from the contract. Then they provide the test command in order to test your exploit. Over on luckyspin.sol, it's a fairly small contract. It gives us a couple state variables, a spin method, and they have a receive function. The variables themselves just dictate cost per spin and the reward. The spin function, we're asked to pass in a number, and then we hit a guard. That number itself, as it's stated in the README, does need to be between 1 and 100. And then the value that we pass has to be equal to the cost per spin. So assuming you get past both these guards, it then has its randomness logic for everyone to see here on chain. So they just made it deterministic. So we will be able to exploit this. This is the vulnerability right here. Now, it should be mentioned, obviously, yes, it's deterministic, and miners can influence it, especially when you keep your logic on chain. A better approach would have been to use something like Chainlink's VRF or maybe a commit and reveal scheme. Nonetheless, we are going to pass a number. We're going to exploit this to ensure the number is correct, and then the guessed number will equal the spin, and we will be transferred the reward. You'll notice they're not only transferring us a reward, but we also get our money back, the cost per spin. So we will be given absolutely everything, and nothing will be left in this contract. So over here on luckyspin.t.sol, they've imported the contract, they created a variable for it, created an EOA called challenger, that's us. They define the contract balance, which is 1 ether, and the initial challenger balance for us is 1 ether. Total reward, 0.1, and then the spins is 10. So we're going to have to spin 10 times. And we also have to do that because our total reward is only 0.1. But yet the contract balance is 1. So yes, we're going to have to do a loop and spend 10 times here. The setup, so they deployed the contract. They then ran a transfer to transfer the funds, the initial funds, or the contract balance that is, to the Lucky Spin contract, so that 1 ETH. The challenger then got dealt his initial balance. Then they ran a couple pre-checks, just to determine that the contract and the challenger indeed have the proper balances. Now we have the test attack function, where they want us to apply our exploit code. You can see here, this is my code. I started by just getting the cost per spin, and then I created a loop. We have to spin 10 times, and each time we do, I'm calling roll. And I'm only doing that, this is just a cheat code that you can find in Foundry, just to show how I can control the block numbers. It really is not needed because the block numbers are incremental anyway, so it's going to have the same effect in my test suite. But it is just a way of kind of showing the same thing that a miner would do. Nonetheless, so I use roll, I get the current block number, I add 1, and then I console logged it. You'll see that when we run it, just so you can see the block number iteration count. And now the correct number, this is our guess. Again, remember that we have the ability to just copy what they're using and then manipulate it for our sake. So I didn't have to do anything. I literally just copied it over, passed my block number in, and then I applied that as the correct number to the spin. So yes, down here, we have to prank ourselves because that was not defined for us up top. I call spin, pass in the cost per spin, and then our guess. We know it's going to be correct, and then it's going to be correct 10 times in a row. We will have to pass these assertions. The first one here is taking a look at the challenger's balance. So this is after running the attack, obviously. He started with 1. And then his expected balance is going to be the initial balance plus all the rewards. And they equal out to 1 ETH as well. So his balance at this point will be 2, and we expect it to be 2. The final assertion here takes a look at the balance of the Lucky Spin contract. We just siphoned all the funds out of the account. So we now know that that's 0. So we expect it to be 0. All right, so let's see this in action. I'm over here on the terminal. I'll run the command. All right, so we did pass. And from the top here, it starts with logs. This is simply logging our new block number. So this is where we did vm.roll plus 1. This was just for transparency. The trace logs start by telling us that our cost per spin. So yes, we did get the cost per spin. We use vm.roll. vm.roll showing you the current block number. And remember, we added +1, and then we logged it. So we're using block number 3. And then we had to prank ourselves. So for each iteration, we had to prank ourselves. We then called spin, passed in the cost per spin, and then our guess. Now, it might be a little confusing because the block number, you may assume we passed in the block number, but we did not. It just worked out that way. This indeed is the result of our deterministic equation for our number. So we passed it in. We know we're going to be successful. Then the contract then gave us a reward, and it's going to be our cost per spin plus the reward. So if you're wondering where that number is coming from, and then we had to do that at 10 times. So as you can see, success on each iteration. And now at the bottom, right here, we have 2 assertions. So indeed, this is the challenger. We expected that he'd have 2 ETH, and indeed he has 2 ETH. And then this final one here is the contract. We expected 0, and indeed it has 0. All right. So I think one thing I can do here is I'll clear this terminal. We'll go back and just show you right here. We did not need this. I just added this in, like I said, just kind of show that we have a way in testing to manipulate the block number, but it won't make any difference whatsoever because everything's running in our test in a sequential order anyway. The numbers would have been sequential. So here, if I run this, you see we get it all the same again. All right, so that was my approach to solving the lucky spin exploit. If you had a different approach, I'd love to hear it. Or if you want to discuss my approach, feel free to grab my contact information. You will find that in the description below. See you in the next one.